Hello and welcome to another Arlington High School Math 4 Honors lesson. I'm Kirk Weiler and today we're going to be doing unit number 7, lesson number 4, additional related rates problems. This is really just a set of 4 additional problems to get a little bit more work on related rates of change. For students in my class, it's both the work that we're going to be doing in class and the follow-up homework, and it's going to be it in terms of related rates of change. 3 and done. That's a lot of time to spend on a single topic for us. So we're going to launch right into them. I'm going to walk you through the thinking in each one of the problems, but we'll probably move through them fairly quickly. So let's take a look at the first one. A spherical lollipop is losing its volume at a steady rate of 800 cubic centimeters per minute. It's kind of how many licks does it take to get to the center. How fast will the radius of the lollipop be changing when its diameter is 4 centimeters? There's a little bit of a typo there. My apologies. This should be its diameter is 4 centimeters. The volume of a sphere is given by the equation v equals 4/3 pi r cubed. So let's kind of picture this, right? We've got this sphere. I'm going to just draw a little bit of an equator on it so that it kind of looks 3D as opposed to just a circle. And what we're told the volume's going away at 800 cubic centimeters per minute. Seems like a lot. 800 cubic centimeters per minute. All right. Remember, the derivative is negative here because the rate is negative. It says, how fast will the radius of the lollipop be changing when its diameter is 4 centimeters? All right. See if you can figure out the final answer to this problem. I'd like you to express it both in terms of pi and in terms of a decimal accurate to 3 decimal places. Remember to include correct units. Pause the video now. Take up to maybe 10 minutes to do this problem. All right, let's go through it. It's actually pretty straightforward. We know dv dt. We're looking for dr dt. Okay? The linking equation is just sitting here, right? V equals 4/3 pi r cubed. Unlike a cone problem, there is only one independent variable here, and that's the radius, right? So there is no height, it's just the radius, which means we can immediately take the derivative of both sides, dv dt. That 4/3 and the pi are constant, so no worries there. In fact, we get a nice simplification that happens. The derivative of r cubed is 3r squared times, of course, our rate, dr dt. And one thing that we can cancel are these 3's if we so choose, and we'll get 4 pi r squared times dr dt. And that equals dv dt. Now keep in mind that we know this, right? We're looking for this. We don't know the radius, but I think we can figure that out pretty easily, right? The diameter is 4 centimeters, the radius will be 2 centimeters. That's pretty simple. So let's plug all the numbers in, going back to blue, right? And maybe coming up here. What we'll see we have negative 800 equals 4 pi times 2 squared times dr dt. If we just clean up this side a little bit, it'll end up being 8, whoops, no, my bad. It'll actually be 16 pi times dr dt, right? Because we have 2 squared, which is 4 times 4 gives me the 16. So now solving for dr dt, I find negative 800 divided by 16 pi. 16 actually goes into negative 800, and we'll get negative 50 pi centimeters per minute. Negative 50 divided by pi centimeters per minute. That doesn't do very much for me, so I'm going to change that into a decimal. That's going to be negative 15.915 centimeters per minute. And this is actually, I think, a good point to look at this and say, wow, I think that this is a completely unreasonable problem. Sometimes when you're a math teacher and you're making things up, sometimes maybe you make it up a little bit too quickly. I mean, if you really think about it, right, a 4 centimeter diameter is about yay big, right? And somehow we're losing nearly 16 centimeters per minute on its radius. So this is a lollipop that goes like that, very, very fast. Anyway, so maybe not so realistic. But why don't you write down anything you need to, pause the video now, and we're going to scrub the text. All right, it's good to be able to be self-critical. All right, let's move on. Next problem. Sand falls from a conveyor belt at a rate of 10 cubic feet per minute onto a conical pile. Right, conical pile means a pile in the shape of a cone. The radius of the base of the pile is always equal to twice the pile's height. How fast is the height of the conical pile changing when the pile is 5 feet high? As a side note, from a realism perspective, this actually is relatively realistic. And I bet you maybe have even seen this before if you live in an area where there's any kind of a mine or anything, right? You know, these things throw out soil or rock or whatever, and they often do form in the shape of a cone, and very often the relationship of the diameter of the cone to the height or the radius of the cone to the height stays consistent. It's called a slippage angle in sort of engineering. So what's happening, right? We're adding sand at a rate of 10 cubic feet per minute. All right, and we want to know how fast the conical pile is changing when the height is 5 feet. So what we need is a formula that relates the volume to the height. So V equals pi r squared h. All right, now, like before, what we know is that dV dt, that was my great how can I live without her office assistant, Debbie Elder. We know that the volume of the pile is increasing at a rate of 10 cubic feet per minute. We know that the volume of the pile is going to be given by pi r squared h. All right, what we want to know is how fast the height of the pile is changing. So we want to know what dH dt is. And this is kind of a classic cone problem because, again, we have too many variables. We want dH dt, we know dV dt, we don't know dr dt, and we don't care about dr dt. But what we're told is that the radius of the base is always equal to twice the pile's height. So the radius of the base is always equal to twice the height. What we're now going to do is we're going to use this relationship the way we have in other cone problems to actually eliminate the r. Notice that it's often the r that we're getting rid of. Not always. There could be situations where we're curious about that as well. But I'm going to put this in, just like other cone problems. What I'm going to do is I'm going to clean this up a bit. I'm going to square the 2h. Watch out, make sure that you square the 2 as well as the h, otherwise the 2 gets offended. You don't want to offend 2. We'll bring that 4 out, 4 pi h cubed. So the great thing about this formula now is it's kind of like exercise number 1. The volume of our conical pile now only depends on one variable, and that's the height of the pile, no longer the radius. This is great because now I can go way up here and I can immediately take the derivative and I can find dV dt equals 4 pi times 3h squared times dH dt, right? Just very simple. Maybe do a little bit of cleanup work here. dV dt equals 12 pi h squared times dH dt. What do we know? What do we not know? Let's check this out, right? We know dV dt. Let's see, we know h. That's good. And we're looking for dH dt. Plug and chug. Let's do it. All right, dV dt is 10. H is 5. If I clean up the right side a little bit, what I'll get is I'll get 25 times 12, and that will give me, I don't want to think about this. Oh, wait. 100 pi? Yeah. dH dt. Something doesn't seem right about that. Oh, I'm looking at this thinking, that's not 100 pi. I made a mistake. Let's keep track of the mistake. There should be a 1/3 in here. My apologies. So there's a 1/3 here, and a 1/3 here, and a 1/3 here, and a 1/3 here, right? And actually what happens then is this isn't a 12 anymore. This is a 4, right? Because these 3's cancel. My apologies. All right, so we have a 4 here, and now the 100 makes sense. If we divide by 100 pi on both sides, we get dh dt is 1 divided by 10 pi. Okay? Again, not very meaningful to me, so I would change it into a decimal, and I would find that the pile is actually only growing at 0.032 feet per minute. So the fact that the volume is growing at 10 cubic feet per minute, that seems actually very robust. A cubic foot is actually a fair amount of material, and it's very, very heavy, especially if it's sand. But because of the size of the pile, and because a lot of the volume is kind of going into spreading the pile out, as opposed to lifting the pile up, the height is actually growing very, very slowly, 0.032 linear feet per minute. All right, sorry about all those 1/3, but it's kind of neat to track a mistake like that. All right, I don't know why I've got a 4 down there. This is a 3. Okay, I'm going to clear out the text, so pause the video if you need to. Here it goes. Next problem. We're just going to shotgun problems today. All right, because this is our 3rd day. Number 3, a balloon is rising vertically. This is going to be a tricky one. A balloon is rising vertically above a level, straight road at a constant rate of 2 feet per second. Just when the balloon is 65 feet above the ground, a bicycle passes underneath it going at a constant rate of 17 feet per second. How fast is the distance between the bicycle and the balloon increasing 3 seconds later? It is really important to work through what is going on in this problem before you try to solve the related rates. And the interesting thing about this problem is that there's really 2 moments in time that you have to think about. There's t equals 0. All right, we've got some balloon. Maybe draw a string. Right? And what do we know? The balloon is rising at a rate of 2 feet per second, right? And it is 65 feet above the ground, just at a point where somebody riding on the worst looking bicycle ever, I don't know how to draw a bicycle, and much less a person riding on a bicycle, just as a bicycle is underneath it, moving at a rate of 17 feet per second, right? So don't worry about any related rates or what we're trying to find or anything. That's what we know right at this moment. Then what we're really wanting to know about is what's happening 3 seconds later. Right? We actually don't care about this moment in time, but they tell me quite a bit about it. Let's graph what's happened now, right? The balloon apparently has been deformed a little bit, right? Continues to rise. The bicycle, or whatever torture device this is, has moved on, right? Assuming it's still moving at 17 feet per second. Right? And this is when we want to know how quickly this distance is changing, right? The distance from the balloon to the bicycle rider. Now, probably most of you realize already that what we're talking about is a Pythagorean theorem relationship, right? Let's call this y. Let's call this x, right? Maybe I'll call this, I don't want to call it little d. We'll call it c for hypotenuse, because that makes a lot of sense. All right, so what do we know now? Let's phrase some rates. Well, we know, based on this picture, that the balloon is going up, dy dt, at a rate of 2 feet per second. We know that the bicycle is moving at a rate of 17 feet per second. We know what we're looking for. That's dc dt. We even probably know the equation that relates them. X squared plus y squared equals c squared. Finding its derivative is pretty easy. 2x dx dt plus 2y times dy dt, a beautiful y, equals 2c times dc dt. Now let's go through our checklist. What do we know, what do we not know? We know dx dt, we know dy dt, we're looking for dc dt. And you know what? We don't know any of the other ones. Don't be fooled. Don't think that y is 65, right? It's not. Don't be looking at the picture with t equals 0. So what I'd like you to do right now is pause the video and try to figure out what x, y, and c, what all those values are at the 3-second moment. All right, well, let's take a look. X should be easy, right? X is simply going to be 17 feet per second times 3 seconds, and that's going to be 51 feet, I think it is. Yeah. I don't know why I had to look at my notes for that. Y is a little bit trickier. Y starts at 65 feet, but then it gains an extra 6 feet, right? 65 feet plus the 6 feet that it rises, 71 feet. Now, C, on the other hand, is very ugly, and in fact, we would have to figure out what C is by using the Pythagorean theorem. I'm going to just write down what the final answer is. Very, very ugly. C ends up being the square root of 7,642, just found by our good old friend Pythagoras, the Pythagorean theorem. But now we have everything. Boom, 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 right? We can substitute all these numbers into this equation and solve for dc dt. Again, I think I'll skip that particular algebra. It's pretty ugly. Well, it's not all that ugly. It's actually quite easy, but it's just messy. And what we find is that dc dt ends up being 11.542 feet per second. This is a particularly challenging problem for folks because they actually have to think a little bit about the motion that's occurred between 0 and 3 seconds, and that can be tough. So pause the video now, copy down anything you need to, and we're going to scrub it out. Okay, got it? Here we go. All right, last problem. This one's pretty challenging too because it's going to involve trigonometry. The minute hand on a large clock has a length of 8 feet. So we're talking about those big clocks that's on the side of a building. Big, big clock. The minute hand has a length of 8 feet. How fast is the y-coordinate of its tip moving in feet per minute when it's pointed at the 4 o'clock position? For this problem, you will have to determine the value of d theta dt in radians per minute. First, think about it in terms of degrees per minute. All right. So let's just get a feeling for what's going on here. Large clock. All right. Just do 3 o'clock, 4 o'clock, 5 o'clock, 6 o'clock. All right, we've got this pointing at the 4 o'clock position, and it's 8 feet long. Obviously, it's spinning around that way, right? And what we want to know is only how fast is the y-coordinate changing. Obviously, the y-coordinate is moving down. Wow. Okay, so look at it this way. Really, all we're doing is keeping track of the xy coordinate on this circle as it sweeps around, right? As it sweeps around. Now, what I'm really hoping is that all my students know the following relationship. Y is equal to r times the sine of theta, where theta is this angle, right? Theta is this angle. Okay, measured positive in the counterclockwise direction. Now, what's good about this is that it involves the thing that we're looking for, right? We want to figure out what dy dt is, okay? But we have to know what d theta dt is, all right? We have to know that. Now, what's cool about a clock is that you can figure that out on your own. So what I'd like you to do now is pause the video. I want you to take some time, and I want you to figure out what d theta dt is in terms of radians per minute. Go for it. See what you can do. All right. Well, you know, there's lots of different ways to go about it. It says first think about it in terms of degrees per minute. I don't think we even need to do that, quite frankly. I'm fairly certain that that minute hand is going to complete 2 pi radians in 60 minutes. Fairly certain about it. Now, if we're really using this equation and we're really orienting ourselves kind of in a polar way of thinking, then the fact that it's moving clockwise, I should really introduce a negative. It's not like the biggest deal on earth if I don't, but let's try to be consistent here. I think I'm going to even reduce that to negative pi over 30 radians per minute, because remember, all calculus should be done in radians. But now we have d theta dt. So let's play around with this, right? We can now use this equation and find dy dt equals r. Wait a second, what is r? R is a constant. It's 8, right? R times cosine theta, right? Take the derivative of sine theta, times d theta dt, right? Okay, checklist. All right, we are looking for dy dt, so no problem. We know d theta dt, but what is theta? What is theta at sort of that 4 p.m. mark? All right, I want you to think about that a little bit, okay? What's cosine theta there? All right, think about that. All right, let's take a look. This is a bit tricky because you really have to think, I'm going to stay in red, you have to think about what this angle is. Now, keep in mind that what we know is that that constitutes, if you will, sort of 5 minutes on a clock, right? That's what it constitutes. So what I'm really trying to do is convert a rotation in terms of minutes into a rotation in terms of radians. So remember, I could just do something like this. I could just do, oh, well, I'll just do 30 minutes divided by pi radians. And what I would find is that that is a pi over 6 angle. And again, technically, it's really a negative pi over 6 angle. Not that it matters that much, but that means we have theta, right? That's it. So we have everything we need. dy dt is going to be 8 times the cosine, I'll put the negative in there, negative pi divided by 6, times d theta dt, negative pi divided by 30. Okay, the cosine of negative pi over 6 is a positive root 3 over 2. So I could multiply all of this out, and it would become negative 0.726 feet per minute. Okay, I'm happy with the fact that it's negative, because at that time, the minute hand should be going down, right? The tip of it should be going down. If we figured out dx dt, which we didn't, but if we did, we'd also find that that was negative, because the hand was moving to the left overall. Okay, that's a challenging problem because it involves trig. You have to think about a lot of the geometry to figure out d theta dt, to figure out theta, but it's all within your grasp. Always say to yourself, when you don't know something, can I find it? Is there some tool in my toolbox that will allow me to solve this problem? All right, so I'm going to clear out the text, pause the video if you need to. Sorry about the camera there. All right, it's gone. And that is it. 3 lessons and a lot of problems on related rates of change. Challenging topic. I hope that my students have watched these videos and have been able to get a little bit more out of them than what we just did in class. If you're watching this and you're not in my Math 4 Honors class, I hope that it helped you with related rates of change. Until next time, I'm Kirk Weiler. Keep thinking and keep solving problems.